What actually happens to your field of vision when you push a spacecraft toward the speed of light? Instead of a simple blur, the geometry of the sky reorganizes itself. As you accelerate, light from all directions begins to focus into your forward path, concentrating your entire perspective into a single point. To see how this happens, we start our journey from Earth, accelerating our spacecraft constantly. Because our bodies only feel acceleration, the physical thrust pushing us into our seats, and not the velocity itself, the sensation inside the cabin is entirely normal, no matter how fast we eventually go. Outside the cabin, however, the environment becomes hostile. At extreme velocities, striking a tiny speck of dust carries the kinetic energy of a massive explosion, tearing through a metallic hole instantly. Surviving this initial phase requires engineering an advanced force field just to sweep the flight path clear of stray debris. Navigating these kinetic thrites below physical friction of deep space is a mandatory requirement before encountering the laws of relativity. At these initial speeds, the changes we observe are purely optical. They result from the way our ship intercepts light rays, leaving the physical structure of space untouched. Look at this diagram. If you are driving a car quickly through a rainstorm, the rain falls straight down, but your forward motion makes the drops hit the windshield from the front. The faster you drive, the more the rain seems to tilt sharply toward you. This exact same geometry applies to starlight, creating what physicists call the aberration of light. Starlight originally coming from all around the ship appears to stretch and gather directly in front of the windshield. As you plow into these forward light waves, you compress them. This is the Doppler effect. The compressed waves shift toward the blue end of the color spectrum, making the light from these stars seem brighter. Looking forward, the clocks on those distant stars appear to tick faster. At the rear of the ship, you are outrunning the light behind you. Those waves stretch out, shifting toward a dim red color and creating the appearance that everything behind the ship is operating in slow motion. These visual shifts are intense, but they are optical effects based on how our eyes intercept moving light. If you cut the ship's engines and drifted to a halt, the sky would return to its original state. As the ship pushes closer to the speed of light, these optical shifts give way to physical, measurable changes in the environment. This graph maps out our universe, using 3 dimensions of space and 1 of time. On Earth, we move along a standard timeline, but at extreme speeds, our ship's trajectory through spacetime begins to diverge sharply from Earth's. Time actually dilates. The crew aboard this ship is now physically aging slower than everyone back home. Space itself also reacts. Through a phenomenon called length contraction, the physical distance between you and your destination flattens along your direction of travel. The universe shrinks the track in front of you. This creates a direct paradox of extreme velocity. To the crew, crossing 1,000 light-years of distance takes only a few seconds. To an observer watching from Earth, millennia will have passed by the time you arrive. Interestingly, if you passed a planet in this state, it wouldn't look completely flattened. Because the light from the backside of the planet arrives on a delay compared to the front, the heavily contracted sphere creates a geometric effect known as Terrell Penrose Rotation, making the planet look like it has twisted in place. These effects prove that space and time are not rigid structures. They are flexible dimensions that stretch and contract based on an observer's velocity. Even with space flattened and time slowing down, you cannot reach the speed of light. Light is an absolute constant, meaning that no matter how fast you travel, it will always speed away from you at exactly its own velocity. Because you can never catch the light, endless acceleration traps you. As you go faster and faster, your field of vision continuously shrinks forward. This is the final visual state of the universe from the cockpit. Every star and galaxy in front of you is compressed into a single, infinitely bright spot. Behind you, the light can no longer reach your ship, leaving an absolute black void. The speed of light acts as an unbreakable mathematical limit. You cannot cross it. You can only approach it, moving through a severely contracted universe. While nothing can move through space faster than light, the theory of general relativity allows space itself to move at any speed. Here's the concept of a warp drive. Using negative energy, a ship pinches spacetime, compressing space ahead and expanding it behind to surf a geometric wave. Incoming light rays strike this curvature, bending around the bubble, entirely distorting the ship from view. Looking out from inside the bubble, you would see a blindingly bright star field directly ahead and a permanent cone of absolute invisibility trailing behind you. That cone exists because the ship is outrunning the information behind it. The light emitted by the universe in your wake is moving too slowly to ever catch up and reach your eyes. Reaching for the speed of light shows space and time are not fixed constants. They are flexible dimensions that transform according to the observer's velocity.